Okay, so let's start. So thank you very much for inviting me to this webinar. I'm glad to share with you guys and then what is the Izon workflow for the exosome purification and quantification. To start with, let's see some background information. We know that there are plenty of EV isolation methods, from differentiated centrifugation, density gradient centrifugation, side seclusion column, or ultrafiltration to immunocapture and precipitation. And then all this method has this advantage and disadvantage. Regarding for the centrifuge method, we know that there are like a high centrifugation force will lead to some damage to the exosome surface, so it's not recommended. Also, for example, like the differentiated centrifugation is also bring down contaminated proteins, which means you co-isolate together with your exosomes. And for the density gradient certifications and the density solutions that such as sucrose, we may interfere further downstream analysis, for example, RNA study. As to the ultrafiltrations, it's based on a molecular weight cutoff membrane. There are two types of ultrafiltration filtration. One is dead end, one is cross flow. At the dead end, as you see, it will accumulate on the membrane, which will lead to the membrane clog. And it also applied force to it. It will also lead to some damage to the exosomes. As to the cross flow, so the flow direction is not the same as the membrane directions. So it will gradually help to remove the small proteins. It's more efficient. But this one is only considered as a concentration method. It can help to remove some of the little protein, but still maybe around like 30 to 40% protein contains in the cross flow. So this method is usually used in combination with other methods such as chromatography. Usually, for example, we do the cross flow first and then do the side exclusion. Immunocapture, this one will give based on the antibody affinity to the antigens on the EV surface. It can give quite a pure fractions. But the drawback is that it's quite expensive. You see that the antibodies resiliency is very expensive. As to the precipitations, it's some kind of, we can also consider it as a concentrating method because it uses the polymer or to down the exosomes, but it also will put down lots of like contaminated proteins, which need further purification. As to the size exclusions, it's a very gentle method because, for example, like our qEV, we run the column in gravities, and so it will, and also in PBS buffers, so that, which means it will retain the activities of your exosomes. So the size exclusion column has the size exclusion beads. The beads contains lots of small holes inside, and when you put your sample through the columns, all those small impurities, including your protein or some of the dye, it will trap in the beads, and your EV and all exosomes, large particles, will go through the size exclusion beads, and then it will elute first. And all those impurities will trapped in the holes, and then it will take a longer path to flow to elute, and it will elute later. How it looks like? So you can see it looks like this, and then your large particles will elute first, which is in the default PCV, and then the impurity, including the proteins, which has very small size, and it take a longer way to go, so it will elute later. So you see, by these physical principles, it separates your exosomes with the proteins. So it's very gentle and it's a physical method. As to isolation, EV isolation with our qEV systems, this is our standard workflows. So our columns can accept different biological fluids, including plasma, cell culture media, urine, and any fluids can be used the qEV columns. You can either manually use the column, or for small research scale, small volume, you can use our automated fraction collector, AFC. It's automated the qEV runnings. qEV when you apply your sample to the QVs, you can get your purified versions and then analyzed by our particle analyze techniques, and also some downstream study, for example, protein study or RNA studies. Our current prepared columns including the following. From the smallest one is 0.15 mil loading to the largest one is 100 mil loadings. And each column has 3 types of gel type: 35 nanometer, 70 nanometer, 20 nanometer. You can see for the cell culture medium, we usually recommend the 35 nanometer resin. And for plasma, you see here, we usually recommend the 70 nanometer resin. For researchers want to do small EV studies, we recommend using the 20 nanometer resin. So our columns provide very high purities and then the yield. You see here, the yield is quite high. And 35 nanometer resin provides a middle level of yield. And then as to the purity, you can see it's different. And then the 70 nanometer resin give you the highest purities in units of particle per microgram protein. You can see it's almost reached around 4 to 8 to the power of 9 particles per microgram proteins. 35 nanometer resin is in the middle, around like 2 to 4. And the 20 nanometer resin is the lowest, it's like around like 1 times 10 to the power of 9 particles per microgram protein. That is because of the different resin, different hole size. And the 20 nanometer resin have the smallest hole size, and then which will include some of the impurities. So nowadays, for most of the cell culture study, we recommend using the 35 nanometer resins. And also for plasma samples, one of the contaminated proteins worry the most researcher is the lipoprotein. As you see, that is qEV remove of most of the lipoprotein, which have the ApoA1 marker. You can see, even though it's quite high here, right? But you see the y-axis is only around the 0.003% of ApoA1 remain purified by colon our 7 nanometer regimes. And as to ApoB, so you can see the 17 nanometer also removed most of it. It's only around less than 2% remains 7 nanometer regimes. And for the 20 nanometer resin, 17 nanometer, 75 nanometer resin, they're slightly higher. It's around 6% remains. And all our column, as mentioned, can be run manually. So if you're checking our manual, each manual has its own buffer volume. Buffer volume means once you add your samples, it is the volume won't contain any of the exosomes. After this, you should, and we suggest to start to collect your exosomes. That is here. Example, take our 0.5 mil loading column, for example. When you load your 0.5 mil of sample, skip the first 22.5 mil, and then we suggest to collect the 1.6 mil of PCV as your purified versions. Later, you see the protein start to increase. We don't suggest to collect this part, and you get very purified fractions for the 1.6 mil that is here, high purity. And column can also be run together with AFC. AFC enabled automatic running of the columns, and then you just program it, and then it can run the column automatically. The AFC support columns from the 0.15 mil loading to 10 mil loadings. You can see that we can set the collect volume and buffer volume here. So you are interested to analyze your collection from the start, you can also zero the buffer volume. It will collect the fractions from the moment you start to add your samples. So it's a very convenient tool to help you to automate the EV collections procedures. Previously, we just talked about the lab scales, which using either minute collection or AFC collection. As to the EV isolation scale up, which have 2 directions. First direction is to scale up for diagnosis studies. How do we do that? Usually, for diagnosis, it requires small volume to detect the biomarkers. which means that we usually recommended of using the qEV single, qEV original, qEV1, which has 0.15 mil loading, 0.5 mil loading, and 1 mil loading. And we developed this robot systems. It can support 12 of the qEV original, which have 0.5 mil loading, and 24 also can support 24 qEV single, which has the 0.15 mil loadings. And it automated these procedures because like with the AFC, one AFC, it can only do one sample at a time. If you have like 10 sample, 10 sample want to do, patient sample want to do, you definitely won't want to buy like a 12 AFC and then touch the touch screens 12 times. With the robot system, you can see that it replaced this work. You don't need to use like multiple AFCs anymore. You just do with one of these robot systems. It can help you to deal with multiple samples. We recently installed a Dexter device in a hospital in Taiwan. So the customer have 700 patient samples, and he used our qEV single 0.15 mil loading columns, and then use the Dexter to run. One you see in the picture is a customer from German Brain Institute. They used our AFC to publish this paper. You can see the diagnosis study, quite high impact factors. And they are very satisfied with the qEV columns. And later they progress to, previously they have 12 AFC, and then replace this one with the Dexter systems, which will assist them with more sample running and then improve their sample processing abilities. And then, as you see, the robot system helps to automate all the procedures. You just need one laptop to program it. On the right, you see is running now the 11th sample, and then you can see the green one means the sample already finished. In the video on the left, you see that it's the procedure is automated. Left side is where you put your sample. One row is 12, two row you can put out like 24 samples, which means it can handle 24 samples at a time. We just talked about the scale up for diagnosis. And as to our solution for EV solution for therapeutic, which means that usually it means large volume cell culture media. How do we achieve that? First, with the introductions of our GMP-ready columns, so which columns have the test endotoxin level and the microbiome levels, it is safe for you to use in such studies. So it's GMP-ready. And our standard approach for this bioprocessing workflow is like this. Same, we accept like different types of biofluids, and we use our qEVTFF engine flow filtration system to pre-concentration, pre-clarifications. After that, we use the concentrated cell culture media and put it into our large columns together with our qEV Zenco를. It's called our like automated chromatography systems with large columns, and we use our particle analyzer for QC check of the size, concentration, and also can do the zeta potential, because zeta potentials indicate the stability of the particles in the solution. Sometimes it's used as a QC purpose. The general step is look like more detail. The general step is look like this. First, we just to do a clarification step. We use different type of size of filter. In this case, it's 30 micron, 10 micron, 5 micron filter to do the sequential filtrations in more large particles or cell fragment. Sometimes if you culture with the, for example, macrocarrier, for example, if your sample contains like 100 micrometer microcarrier, you will need to change this filter to large one. For example, change it to a 70 micron filter. After this one, and you process your sample to the hollow fiber, and then to TFF system, which do the concentration step. The hollow fiber has the molecular cutoff. Usually we suggest to use the 100 kDa or 300 kDa for exosome samples. System will enable concentrating your samples, and then for those particles less than the molecular cutoff, it will be elute into the permeate and the waste line, and then this line volume will become larger and larger, and the circulate volume will become less and less, and then your sample will be more concentrated. After concentration, we put your samples from your sample to our Zenco system together with the qEV columns, and then enable automatic run of the purifications. System we will talk about later. It has the UV sensor which will guide the collections of your purified volume. Because the AFC we just talked just now is based on the weight, and then based on the preliminary studies of our internal study to find that where is the buffer volume. But this one will be more accurate to guide through the UV sensor. And sometimes if after the qEV columns, you feel like you still need to concentrate your samples, we can do a post-column concentrating to reach even higher concentration factors. And if you think this one is all the procedure is not so difficult, no. So the scale up is all about the process of optimization. So optimization is also started from choosing the filter size, molecular cut-off size, surface area, and what column to choose, because there are different loading volumes. For example, as you see here, our 100 kDa membranes will have the very high recoveries, but it takes a very long time to procedure. And the 300 kDa is the median hole size. It also has a high recovery. It has a better proton removal, and then in the middle processing time. And for the membrane of 750 kilodaltons, it has quite a large pore size. This one, by using this pore FF hollow fiber, it can process the sample very fast, but it has a drawback. It can remove more of the free proton, but it will also remove some of the exons, because like 750 nanometer kilodalton, 750 kilodalton will also remove around 30 to 50 nanometer particles. So it depends on your applications, and we will decide which membrane, which molecule cutoff to choose, and also we will also need to choose the surface area. To be honest, the larger the surface area, the less chance of blocking the resistance. The large surface area, which means like the large, like the hold up volume, and then more like a waste of money. So that's you need to make a balance. So as to our pre-palette scale, we just use, like for example, the TFF system to concentrating, and using the chromatography system for purifications. So this one will include can support our qEV 10 column, qEV 100 column, and even qEV. This system can support up to qEV 400. And this is our qEVTFF system, like tangential flow filtration systems. On the left, you can see there are two scales. One is to weight the sample. The other is to weight the permeate. Your sample will go through the channel and then return to this line, and then through the hollow fiber, anything which is smaller than the molecular cutoff, and then buffers will go through to here, and the waste will become more and more, and then your sample will be more and more concentrated. Also, the system can support from 0.5 liter to 15 liters. And for small amount of sample, you can just use like a lab scale bottle, 1 liter bottle, 2 liter bottle. But for larger scale, okay, this is showing what it looks like. Feed line, the hollow fiber, the permeate line, retentate. These two lines, feed line and retentate, on the same sample vessels, and then because it makes a circular, and this one will move to the waste. And as I said, like the small volume, you can use just a lab scale bottle. For large volume, for example, if it's over 5 liter, over 10 liter, you can use like the processing bag, which can connect to the systems, and then also keep it sterile. This is an example of concentrating around 10 liter of cell culture medium. You can see, and then it's more concentrated. The color is quite heavy now. And as to, you may ask why we need to concentrate the cell culture medium with the TFF first before loading to the chromatographies. As you see here, and if the sample is not concentrated, you can see the yield is very low, and then also the protein peak is quite high. And then because which means the site exclusion columns after site exclusion, the concentration will be even low. We know that the site exclusion have the drawback of dilute samples, but you see these two after TFF concentrating, and you can see remove some of the proteins and also get a high yield of purified exons. You can see two peaks is well separated. You can get your very pure UV fractions here. And so let's say a case studies. And for example, if not use the TFF system to concentrate and then passing the column directly, this sample reached have a concentration of 1/11th. But with the TFF system concentrating and then run through the columns, you can see the purified fractions have like higher concentrations. Also, regarding the purities proves that the after the qEV columns is have high purities. Usually, we consider over 10 to the power 9 particles per microgram proteins is quite pure, and in some cases we can easily reach like 10 to the power of 10. But that one needs a special customized column with longer length. If you see some like other instrument which is that they are like purities below like 10 to the power of 9, you may consider it's not that pure. Why? Because you see here, after TFF systems, you can see the purity is around 10 to the power of 8, which means that if 10 to the power 8, as I mentioned before, it still contains some of the contaminated proteins, which needs the size exclusion column or any other chromatography to further purify the samples. And then with the TF, we just talked about our TFF system, and then let's go to our Zenco system, chromatograph systems. And it support column you can see here from qEV2, 10, 100, 400. 400 is a customized columns, which is order's own request, because like its loading volume is 400. If we concentrate the sample 15 times, you can see that it's actually fitting 8 liters in one run. If you do multiple runs, you can see that this column can fit like maybe around, if you do like 3 runs, it can support like over 20 liters of cell culture mediums. Device have 8 inlet and 8 outlets. It has the UV sensor to detect the EV peak. We usually use 280 nanometers wavelengths to detecting the EV peak. It has multiple sensors to control the progress. This is how it looks like. On the right side is a case study. We run like a 2 liter, 2.5 liter culture medium through the TFF system and then load. We concentrate 2.5 liter to 100 ml and load to this one. This one is a qEV 100. Is 100 ml loadings. So you can see on this laptop. So the laptop controls the Zenco and then automate all the procedure at guiding the picking of the EV peak. So that's the software of this Zenco system. You can see, unlike any other protein chromatography device, this one is optimized just for the EV and or LNP studies. You can see the workflow is very simple, and also method part is simple to edit. We also have different templates for different columns, like qEV2, qEV10, qEV 100. You just need to use the correct template and then to automate the procedures. Like as shown here is an example. You can see that it's automated the procedure is run multiple runs of by the chromatography systems. The first one is the EV peak, the later one is the protein peak, and the UV sensor guiding the collection of the EV peaks. And here I'd like to share some of the bioprocessing case studies. And then we did some like a milk study, 1 liter milk, and then concentrated cell culture medium, and also plasma, you can see 6 liter. This one is highly concentrated cell culture mediums, concentrated like 40 times. The original volume is over like 200 liters. And for the milk UVs, usually we will need to remove fat and then remove the casein. This one can be removed by adding the acetate acid and then to precipitate it, and then run through the columns. You can see the next step is run through qEV columns. And then if you need to post the column concentrating, you can do further concentrating here. And here's the milk UV study example. You can see now with our standard workflow, PFF and chromatography system, you can see it's reached the purity of over 3.3 times 10 to the power of 9 particle per microgram proteins. And you see here, initial raw material purity is only just around below 2 times 10 to the power of 7. It's increased more than 200 times of purities of the milk UVs. And then interesting things you can see here. This one is the raw milk. This one is adding the acetic acid to remove the casein. You can see the casein here. So because we know the casein has the potential around -7, so you can see compare with the raw milk, which is yellow, and then processed milk, and then acetic acid treated milk. You can see a detailed potential shift. This part is the casein. As to the cell culture medium processing, you can see that one by small columns, it also have you can see the EVP, illusion peaks almost merged together, right? Which means the high accuracies. And for our large column, with 200, you can see here, it's running like 20 times. And then with the 2021 times, you can see the start to shift, which means like the lifetime is around like 20. If on the system is easily around 20 times for this sample type. It really depends on different cell culture medium. Samples is slightly clean, which means the lifetimes of the column is slightly longer. You can see the purity of raw material is quite high. It's around 8 times 10 to the power of 8. As to you can see after the qEV 200, the purity almost reached the 10 to the power of particles per microgram protein. That's very high level of purities. Also, as to complex samples such as plasma samples, and then this approach also works. You can see that it's well separated of the EV peak and the protein peak. Here is an even larger column. EV peak and the protein peak is well separated. We suggest to collect the gray part, and you see how this procedure works with the Zenco system. It's easy for your QC purpose to guiding you what is the status of each round. If these merge together of these curves, which means like the column performance stays the same, it's high accuracy to evaluate each round of performance. Here is another two example. For this one, we did a 4-liter cell culture medium concentrating in clean room environment, and these samples we sent to animal trials. And then for this study, we used the GMP-ready columns. As you see that the chromatography will guide you. First peak is the EV peak, the second peak is the protein peaks. And then we calculated the purity from each step. You can see the purity start to increase. Raw CCM is very low, post-clarification. Post-TFF increased. And then post-QEV column, you can see it increased almost around 8 times 10 to the power of 9 particle per microgram protein. That's very pure. And then this customer requests to do a post-sterilization filtration. After this one, you can see that because like the sterile filtration will result in the loss of EVs. That's why you see that usually we use a 0.22 micron filter for this purpose. It will trap some EV and the loss of some particles, and you see some reductions of the purities. But you see the definitely above like 4E9 particles per microgram protein for these studies. And later we did a 15-liter study for the same customers. As you see that the purity increased. And then this is the final product. You can see it's like nearly like a white purified exons. And the purity is higher than 2E9 per microgram proteins. And for even larger scale, for example, several hundred scale. The procedure is similar. Still, clarification by using like a sequential filtration to remove those like cell culture, cell waste, cell fragments. Because by using such filters, it can scale up. By calculating the surface area from your like a small scale trial, you can proportionally increase the surface area, which we are fitting for large scales. And after this one, you do the concentration step. And usually there's another step. During the concentration with TFF, we do the diafiltration. For example, we usually suggest to 20 times concentration together with like around 5 to 7 times of diafiltration. Diafiltration will help to even further remove the contaminated proteins to increase your purities. And the last step is isolation with our chromatography system. The one you see here is an even larger system called a big Zenco. It's handling large column which have 3-liter loading volumes. So we see this is a manual hollow fiber system. So it's a large hollow fiber can handle like several lots of liters of the cell culture medium. This one is our largest qEV columns. It's qEV2700, which means it has a loading volume of 2.7 liters. That's when you see the pink, the red one is passing through the cell culture medium passing through, concentrated cell culture medium passing through it. Here is our largest systems. It's like a GMP grade because of course it's usually shooting for the purpose of GMP manufacturing. It has a flow rate of 1.5 liters to supporting the large column as mentioned in previous slides. The workflow, as I mentioned, is still the same, but it's just slightly different. We use like 2 lines of filtration lines. In case one block, you can easily switch to others. And you see here we use different. This time we use 4 different filters. This one I think is a 70, 30, 10, and 5 micron filter. After this concentrating, and then move to the chromatography for concentration. As you see, the purities increased a lot. As you see, the membrane-based method is just a concentrating method. It still got very low purities. Only after chromatography, you can get even higher purities. And then you see is another case study of running like 30 times. As you see, that is a variation of each round is within like 25%. And the final purity is still acceptable over E9 level. It's quite high. And then that's we talk about our workflow for purification. And then you definitely need to quantify your purified samples. How do we do that? We have 2 devices. The first one is our old device it's called Exoid, based on TPU plastic nanopore. Recently released our silicon pore-based Pulsoid last month. So you can see the current range of it is slightly different. Exoid have different nanopores, which can analyze from 50 to 11 micron. The Pulsoid system currently pore is currently only one. Its range is around 40 to 160 nanometers. This one is mainly for LNP. And then we are releasing the 300 nanometer pores later in June. So which means that you can use this one for EV studies. And then we know that the different types of particle analyzer. They are light-based, optical-based, and non-optical-based. Optical-based are all based on Brownian emulsions. And then based on this formula, you can see that it's measured just the hydrodynamic diameter. It's not the actual size. It will rely quite on temperature, and then, for example, rely on the viscosity of the solutions. And then the limitation of those systems is it measures the hydrodynamic diameters. And then their bias is get a larger size than the actual size. And on the MySafe guidelines, it lists all these limitations to it. So basically, you should use a method to cross-check your analyze. So If you use one light method, optical method, you should use another non-optical method. So our TRPS technology is the non-optical method. Our method, the MySafe guidelines, that is RPS measurement, have very high. It is the same as the TM dataset as you see in the MySafe guidelines. So our old Exoid system is based on the nanopores. So each particle passing through the nanopore, and the block size, the larger it is, the larger the size is. The frequency, which will represent the concentration, and the time of the particle taken to passing through the pore will reflect its zeta potentials. And then we measure the standards, and which has no size, concentration, zeta potential, and use that one to calibrate for the samples. And then Pulsoid를 analyzer is our new generation of device. And then it uses the similar RPS technology, resistant pulse sensing. Currently, it's 40 from 40 to 160 nanometers. And then we will release the next 300 nanometer pulse to support the Exosome studies in around the June time. And then the good thing is that the throughput is very fast. We can say that if the sample is within the pore size, it just takes 2 to 5 minutes to analyze it. And also, for the sample volume, it's 17 microliter. It's non-destructive, which means you can take out the samples after analyze for your downstream, like a protein study or RNA extractions. As you see, the accuracy of the system is very high. And then when we analyze the calibration particles, you see the variation is below 2%. So the accuracy is over like 98% of true values. And also, as to analyze instruments, we need to have a good linearity. So you can see the linearity of this device is quite high. You can see the R-score value is larger than 0.99. And also, what data we generate? What you see is each particle we analyze, which means we are techniques to give you single particle resolution measurements. You can have each particles with its size and its zeta potential. It's very important in some formulation studies. We can detect a tiny change in the solutions. As this shows that the procedure is very short. It just takes 5 to 10 minutes to set up time and 5 to 5 minutes to analyze times. As you see here, this one is studied for the lipid nanoparticles, LNP studies. You can see that we detect a tiny change after freeze-dry. So you can see the particle start to merge together and the size get larger and larger. We can detect such a tiny change. Also, you see here, this is to prove that the high accuracy of this and sensitivities of these techniques. And some optical method just give you a raw peak. You don't know what's the tail distribution of the samples in your sample. And here you can see you can output the zeta potential this particle versus the potential of each particles. As to the principle, it's quite simple. It's like we use silicon chips and assemble it into our flow cell. And your sample is placed on the right side and then passing through the flow cell chips and then go to the left side, is buffer side. And the system will record the electric signal of your particles. And then this system is also rely on the standard calibration standard. And the calibration standard is NIST traceable. It has the accurate no size, concentration, and zeta potentials. This is the actual example as shown just now. So it's a accurate record each blockade of your particle informations, and then can convert it to this histogram. And then it uses a similar principle to measure the zeta potentials, because zeta potential means is related to its surface charge. And the surface charge, when under different voltage, the speed of each particle passing through the nanopores, the silicon pore will be different. By measuring such difference, we detect the zeta potential. Here is a small video to show how the system works. If you can please have a look. The good thing with the chip is that it's only size won't change the whole size because it's a glass hole. It's glass hole. As you see that the procedure is very simple. Just apply buffer, doing the calibrations, and then after the calibration measurements, wash the flow cell, and then apply your samples. So it takes less than 5 minutes for if the sample concentration is enough. So this video is recording our beta unit. Our new unit is slightly different. We have a better design of flow cell, which have later some better the cassette. Now you see there each particle, a calibration particle passing through the pore now. Can start to recording. So the video show you how easy this system is running. It's assembling and then adding sample is very easy. So thank you very much. That is all the presentation today. Thank you. Any questions?
Thank you, Haoyu, for your presentation. Q&A 시간을 가지도록 하겠습니다. 화면 하단에 Q&A 아이콘을 누르고 채팅창을 통해서 질문 주시면 하오유 박사가 확인하고 답변을 줄 수 있습니다. 혹은 손들기를 누르면 저희가 발언권을 또 드리도록 하겠습니다. 아마도 채팅 궁금하신 사항들은 있으신데 채팅창에다가 이제 채팅을 이제 쓰는데 시간이 조금 걸릴 것 같습니다. 채팅창에 채팅을 이제 질문을 하시는 동안에 제가 한 가지 질문을 좀 해보도록 하겠습니다. Haoyu, I have one question.
Yeah.
The qEV column provides a constant result across sample and offers a high purity, which is a clear advantage. However, since the EV is eluted in buffer, an additional concentration step may be required. And our almost university customers use from qEV original to qEV 1. So could you please recommend a suitable concentration method for this customer?
For qEV original, qEV 1, which means your original cell culture medium, maybe like a 20 mil, 50 mil, you can use there's a 50 mil molecule with cut-off columns, spin column. You use that one to concentrate your samples. So it's like, so it's in the 50 ml vacuum tube, the loading volume of that molecular cut-off spin column is 15 ml. So you just do that like if you more than 15, for example 30 ml, you just do the concentrating twice. It will be okay to load to the columns.
Okay. And the qEVTFF data clearly show a separated graph between the qEV peak and an EV peak and the protein peak. Can we separately collect the fraction corresponding to the EV peak and the protein peak when using qEVTFF?
qEVTFF is just for the concentrating. It's not purifications. So we use the qEVTFF to concentrate for large volume. As you see, the qEVTFF system is suitable for concentrating from 0.5 liter to up to 15 liter, 15 liter. So usually for large volume, if your volume is below 0.5 liter, you can easily use the spin column to concentrate. Or there's a manual operated TFF hollow fibers we can like introduce to you. That one support 100 ml loadings at a time.
Okay.
Yes, I saw there's a questions. 200 nanometer also fine. So there's a question say, in the question channel asking qEV column how big of the particle can be allowed in this. As you, I can share the screen again. As you see here, so that here is the recommended isolation range of this of our columns, and your 200 nanometer particles is definitely within the 35 nanometer region. So you can definitely use in the 35 nanometer region for purify your particles. Yes, there are studies or lots of studies apply of the qEV loads on the SDS page. They do the Western blot, investigate the different EV markers. They are all, we can send you some, and then they are like a positive, like the exosome markers. Oh, thank you so much for this comment. Thank you. So any further questions?
Okay. One more question.
Yes, we provide hollow fiber, but it's not manufactured by us because there are so many hollow fiber manufacturers. We choose some we use for the processing job. Our processing job, we know that because we assess the quantity of different hollow fiber. We just choose some which have good performance. If you need, you can get in touch with Phi Korea. We can recommend it to them, and then they can recommend it to you. Because like we have our particle analyzer, we use it to calculate the recovery of different hollow fiber. We found some good one and always use those brand for the processing jobs. We don't manufacture hollow fiber, but we can suggest those brand to you. You can just go to those like go to that manufacturers.
저희가 시간이 좀 많이 지났으므로 오늘은 여기까지 하도록 하겠습니다. 필코리아 테크놀로지는 아이존사의 한국 대리점입니다. 웨비나 이후에도 궁금하신 사항이 있으시면 언제든지 저희 필코리아 테크놀로지에 문의 주시면 또 하오유 박사와 함께 답변 드릴 수 있도록 하겠습니다. 마지막으로 저희가 설문을 받고 있습니다. 설문을 주신 분들에게는 감사의 의미로 또 커피 쿠폰도 제공하고 있습니다. 많은 분들의 참여 부탁드리며 이것으로 오늘 웨비나는 마치도록 하겠습니다. 웨비나에 참석해 주신 여러분께 다시 한번 감사드립니다. Thank you, Haoyu, again.
Thank you so much.
Bye. Oh, Haoyu, please
Yeah.
check one question.
Sure. Yes, the pore can be blocked. That's why so need to have different size of pore to evaluate. Because for example, if you have larger particles, you will need to use different slightly larger pore. So our next silicon pore can support around 50 to 300 nanometers. Will include the most of the exon studies, because we know that exon is from around 30 nanometer to 200 nanometers. So we also have like an unblock guideline to how to unblock it. Basically, it's use the negative pressure to wash out, to sucking out of the blocker particles, and then also we can take the chips to DI water wash, which will flush out of those particles blocking the pores. But the things like we will need to pre-identify whether your sample have very large particles, and then choose the correct size of the pore. For example, like the Exoid, we have different size of nanopore to cover from 15 nanometer to 11 micron.
네, 궁금하신 사항 있으시면은 메일로 주시면 저희가 또 답변 드리도록 하겠습니다.
Thank you very much for listening. So yeah, it's my pleasure to present here. Thank you. Bye.
Thank you. Bye.